grinding high-speed steel tool bits. I'm going to be doing this a little bit different than the other kids, so if you're easily triggered, this might not be the video for you. Otherwise, hold on to your hats. It's a beautiful winter morning that I'm about to spoil by sitting down and doing the one video I thought I'd never do. Grinding a single point cutting tool. Rake angles, clearance angles, nose radii, all that stuff. First, and don't get me wrong, there's nothing I love more, but it's a bit of a tricky one to explain via video. It's a rabbit hole full of rabbit holes that have their own rabbit holes with the termite problem. For a home gamer, it's not really complicated per se, but a lot of the nuances one picks up over the years of trying and failing and trying again, well, they're hard to put down in the step-by-step fashion most people would prefer to have. For example, you could grind two identical tools by hand, and they'd probably perform differently. I mean, that's because you're doing it by hand, of course, but that's the context of this video. If you have a jig or a tool and cutter grinder, it's a different story. Again, it's not hard to do, so long as we're not splitting hairs. But keep in mind there's going to be a certain amount of trial and error on your part if you decide to try it. As I mentioned earlier, I'm going to try to convey what's going on a little differently than the way it's usually presented. And you folks let me know how I do down in the comments, would you? Second, there are already quite a few great videos on the subject already out there. I know Mr. Pete has a few good ones, as do the two Toms, Tom's Techniques and Ox Tools. I highly recommend any of their videos on the subject. And at the end of this video, I'll briefly get into carbide and insert tooling. And lest I forget, Adam of ABOM79 has some good content there. And Dale of Metal Tips and Tricks, I believe, had a rep on his show that sort of walked through all the nomenclature. So those might be two good starting points for you. As I said, there's a lot of good info out there already if you go looking for it. Not just on YouTube, but online in general. Before we get into the nitty-gritty, let's talk about why you'd even want to make your own tools. You certainly don't have to, and you might not want to. Just go out and buy insert tooling and you can hit the ground running. But if this is a hobby for you, insert tooling can get expensive fast, especially early on as you break your way through inserts trying to figure stuff out. However, if you have more time than money, with inexpensive high-speed steel blanks, you can make all of your own. I mean, they're like pencils. You break the point, sharpen a new one. Heck, you can even make custom tools that you couldn't otherwise buy. That said, I suggest you start with a mix of both. See what you like and take it from there. But this video is about high-speed steel, so let's head over to the lathe. So let's start at the beginning. In the beginning, there was no heaven and there was no earth. All was without form. And that's how, in 1771, the lathe was invented. Which brings us to right now, where I've got a piece of aluminum in the lathe that I'd like to cut. And in order to do so, I need a tool. A tool can be any material that's harder than the material we're trying to cut. I would have liked to do this demonstration with one of my wife's chocolate chip cookies, but she hasn't made any. In lieu of that, I'll be using high-speed steel. High-speed steel is a steel with very high hardness, wear, and temperature resistance. And with a simple bench grinder, can be formed into a wide variety of tools for turning, facing, threading, radiusing, parting off, etc. You can also get them round and make boring bars, reamers, countersinks, chamfer tools, etc. Tooling for the mill, tooling for the lathe. Those get a little more complicated. Now, although the high-speed steel is harder than the aluminum, it's not the right shape yet to cut it efficiently. But I'm getting ahead of myself. Let's see what happens when we use this high-speed steel blank, as is, right out of the box, with no shaping whatsoever. We're starting from scratch. So just two things before we get into this. I tend to buy larger high-speed steel. This is 1/2 inch by 1/2 inch. Technically, it's 12 millimeters by 12 millimeters. I like to buy stuff in these sizes because I use most of it on the shaper. But in the home shop, especially like on a smaller hobby lathe, 1/4 inch or 3/8 of an inch is usually way more than enough. And more often than not, when you buy these, depending on the brand, the ends are already cut at a slight angle. Mine usually are square in one direction and have a bit of an angle in the other direction, though I have seen them cut at sort of a compound angle. Or maybe you can see it more on this big one. In order to keep that from affecting our little experiment, I've gone ahead and ground one end completely square, or as square as I could. So I took that factory end off. I'm now going to load this in the tool post and we'll see what happens when we try to cut with it. So I've actually never tried this. I'm hoping it sort of serves to tell the story. I've got the lathe set to 1200 RPM. I'm going to take about a 20 thou depth of cut, a half a millimeter. The cutting speed for high-speed steel and aluminum is somewhere around the 500 or 600 feet per minute range. I'm going to hit it with some WD-40. I've always found that to be a convenient cutting fluid for aluminum. That sounded splendid. So although it actually took a chip, it looks like it's tearing it more than it's actually cutting it. In addition to that, I'm sure you could hear the amount of rubbing that was going on, sort of that really pleasant shriek that it was making. I don't know if you can see it on camera, but there's even a bit of a skip pattern here on the surface where the tool is kind of bouncing back and forth against the material. So the first thing I'd like to do is eliminate the rubbing that the tool is doing. And this is a single point cutting tool, so we really only want it to cut in a small portion of the actual tool bit on the leading edge. But before we do any grinding to address that rubbing issue, you may have noticed, or I'd like to forcibly bring to your attention, the fact that our raw stock started off with 2 faces and now has 4, right? So when we started, it just had the OD and the flat front face. Now, because we've created this step, it's got the original OD, the new OD, the same front face, and sort of the very small face on the inside of this step here. So what this tool is doing is actually cutting on 2 edges. It's cutting sort of on this leading edge in the direction that the tool is moving, and it's also sort of shearing its way along, leaving this surface behind. So in lieu of that, we have 2 edges to relieve. 2 edges are participating in that rubbing. I think the first place it's probably most apparent that we need some clearance is right behind sort of the leading edge of the cutting tool. That whole part of the tool that's to the right of sort of the point we want the tool to cut at. So the first grind we'll do is to just remove some material in order to swing that face away from the workpiece, to give it some clearance behind that cutting edge. The other place this tool is running is sort of immediately underneath that leading edge, sort of the side of the tool facing the chuck. Again, it's leaving 2 surfaces behind as it's cutting, so there's 2 faces, in our case, that it's potentially rubbing on. And in fact, here you can even see some of that aluminum has transferred onto the high-speed steel. So just like we were looking at the top, we'll want to grind away some material here so we're providing some clearance, so it's not rubbing there. All right, so we're at the bench grinder, and the first thing I'm going to do is cut that clearance behind the leading edge. Basically take off that wedge so the tip is really the only thing coming into contact with the work. We'll get into those angles in a minute, but for now, suffice it to say that 7 or 8 degrees should work fine. Now, I usually sort of freehand it, but for this video, I'm going to use the tool rest. So I'm going to grind about 7 degrees into the end of this blank. Now, don't worry about doing any damage to the temper of the high-speed steel blank. Like if it starts to turn straw in blue, it's probably still safe. Obviously, you don't want it to turn red, but it'll get uncomfortable to hold long before you could do any damage to the actual structure of the blank. So just dunk it in some water every now and again, and it'll be fine. So I've underexposed this a bit. Hopefully you can see it. There are some very small sparks just sort of breaking that top edge. When you see those really little tiny sparks coming across the top of the tool consistently, you know you've reached the top. You could also just turn the tool around and look at it, but if you see those sparks, you've hit the top. So let's take a look at that. That's about 7 or 8 degrees. There's no more material behind that leading cutting edge, so that part of the tool shouldn't rub anymore. Now, in addition to that, something else that's happened because we're on the tool rest up against a round wheel is that we've gotten a little bit of an angle on the front edge of the tool. So there was our 7 or 8 degree angle at the top, and because we're up against a round wheel, we've got an angle at the bottom. My tool rest, like I imagine most grinders, is about the center line of the tool. So we're above the center line of the wheel. It's grinding more on the bottom than it is on the top. If you're doing this on a belt grinder, you'd want to tip your table about 7 or 8 degrees down. So with one grind, we've gotten 2 relief angles. When we come against the work, This upper left-hand tip is the only thing that's going to be touching. All of this sort of falls away. All right, I hope that made sense. Now I'm going to do the same exact thing, except do it into the leading edge here. It'll look something like that. That's a little excessive, but it's going to be the same 7 or 8 degrees that we just did on the top. And that only needs to go back, I don't know, a 1/4 inch or so. All right, so there it is. I'm not sure if you can make that out. We've now got 7 degrees across the front, 7 degrees down the side, and because we ground up against the round wheel, we've got some clearance top to bottom. So basically we've got it on 1, 2, 3 faces. The closest part of this tool to the work now will just be this tip. Before we leave the grinder, there's just one more thing I'd like to do. Those 2 grinds have resulted in a very sharp cutting tip. Now, I was going to go try this as is and show you what happened, but I'm going to bet you folks are smart enough to follow along. That tip is so sharp, it's going to leave both a poor surface finish and it's not going to last very long. Like, there's not a lot of material supporting that very small edge. So what I'm going to do is just knock the smallest of radii on here, basically along this edge here, just so I've got a little bit of a round to that corner. I still want to leave the top as flat as I can. I still want that thing to end up sharp. I just don't want it sort of as live of a point. Now, because this tip is such a fine, small feature, I've switched over to the other side of the grinder where I have a fine aluminum oxide wheel. You could probably do this with like a bench stone or a diamond lap, but it is high-speed steel, so removing material takes a while. Though we will use one to hone this before we take it back to the lathe. I've got the tool in my vise. Hopefully that keeps it still enough for you to see how subtle that little radius is on the end there. Now I'm just going to hit it with an oil stone, trying not to roll over any of those sharp edges. Now hopefully I'm also conveying the fact that these things don't need to be absolutely perfect. While we're here looking at this radius, the larger you make that radius, the stronger your cutting edge becomes. And usually the better the surface finish that it will leave behind. The downside, of course, is if you're trying to do inside corners, they'll only be as sharp as your radius is big. So before we take this cut, let's just do a quick recap. The tool geometry isn't quite there yet, but we'll see what happens with just these few changes that we made. When we tried it out right out of the box, it was technically removing material, but it wasn't very pretty. It was making some bad noises because it was rubbing both on sort of like the front end and below the leading edge on the left in this image. So we ground that material away, leaving this upper left-hand corner to be the highest point, the point closest to the material. I'm going to dial in the same 20th thou depth of cut and we'll continue on. All right, so I don't know if you'll agree with me, but that's a pretty good looking cut. That hazing you see is just WD-40. But the chip that it's taking still isn't really that spectacular. I mean, it's long and stringy, and it's still pretty ragged. So we're not doing a super clean, like, shearing cut. It's still tearing just a little bit. The chip has, it almost feels like a small hacksaw blade. Now, if we'd like to improve the situation, specifically here in this case with aluminum, we're going to want to make this tool just a little bit sharper. But before we go back to the grinder, let's sit down at the bench and have a really good look at what we're dealing with here. On second thought, we can look at it right here. What I want to show you is the end of the tool. I want to show you what the work sees. In this view, the tool would be moving to the right. The cutting edge is essentially just this small portion up here. The purpose of all the grinding we've done so far was to ensure that. We ground an angle in the leading edge and basically a compound angle in the face to ensure just that leading tip is making contact. Those angles are called clearance, or relief angles. In this tool there are 3 of them, one each in X, Y, and Z. And they made a significant improvement in how the tool works. We also added a small tip or nose radius, so the tool wasn't so wimpy. You ever notice how the tip on a blunt pencil lasts a lot longer than one on a sharp pencil? Same thing. Next, let's look at what the material does when it runs into the tool. Lathe tools are set to the center height of the lathe, and our tool has a flat top. So when the material we're cutting hits that flat top, it has to make a hard 90-degree turn and leave across that top face. It's a pretty harsh transition. What we'll do next is grind a bit of an angle on that top face so the material we're cutting makes a bit of a less dramatic change in direction. That grind also serves to make our tool sharper. The included angle becomes less. Now, since we said this tool cuts essentially on 2 edges simultaneously, we want to angle the top in 2 directions. First, we'll drop the trailing edge about 7 degrees away from the tip. And in addition, we'll also want to drop it front to back 7 degrees. So just how our previous grinds left the cutting tip the closest to the work, we want to do the same thing to the top face. We want to grind away all of the top face so the top of the cutting edge is the first to hit the work. And as material spills across it, it transitions sort of down and away. Now this is going to be a little tricky to explain, but if you try it yourself, it's pretty self-evident. With one grind, I'm going to try to get both of those angles. Now I'm on the fine side of my grinder just because the tail end of the tool touches the body of the grinder and I can't get the angle that I want. But if I were to grind this, this is our cutting edge. This is the top face we want to grind. If I pick it up and I grind against the wheel while I'm on my tool rest, it's going to cut a scallop, right? It's going to be sort of that rounded shape where it's lower in the back and higher in the front. I also want that top angle to lean back a bit, so I'm going to turn my tool about 7 degrees up this direction. I'll grind this and we'll head back over and look at it in the vise. Alright, so I hope you can see this. I'm actually back in the lathe. It's going to end up here anyway. The top surface has now been ground, so it drops away from the cutting tip in both directions. Again, spitballing, it's about 7 or 8 degrees. You can see it more sort of right to left than you can front to back. I should have maybe done a little bit more, but this should be fine. Just like before, I'm going to stone the edge. I'm using a little diamond lap here because I don't know what the happened to my stone. I mean, I was just holding it. Now, the top's a little bit tricky because the grinding wheel left a concave grind. Now, those 2 angles that were just ground in are called rake angles. Before we did any grinding, the top of the tool was flat. And the way it's hitting our work, it's hitting it like at 0 degrees. That's called a neutral rake. As we drop that surface down, as we're sort of scooping into the material, the more and more we drop that, the more and more positive that rake would become. So if the material that you're cutting is sort of making a less harsh transition off of the stock, that's positive rake. If we had ground the tip lower, so the material is not only making sort of a right-hand bend, it's almost making a U-turn when it hits the tool, that would be called negative rake. Now, as you might imagine, the more positive rake the tool is, the weaker the cutting edge is. Like the sharper that edge is, the weaker it becomes. It'll work, it just, might not last as long. If you have a very high negative rake, that tool pretty much becomes like a bulldozer. Now for aluminum as a soft material, high positive rake is pretty good. We didn't actually put that high of a rake on it, 7 or 8 or 10 degrees, whatever they happen to be. Rake also has an impact on the amount of horsepower required to make a specific cut. Again, the more positive rake, the sharper the tool, the less power your machine will need to remove material. It's kind of like trying to cut something with a sharp knife or a dull knife. Now, what those rake angles should be for different materials isn't that complicated, but it's a little bit more than I'd like to get into for a video like this. But suffice it to say, for small hobby machines, positive rake is usually the way to go, in particular for high-speed steel. So I'm going to come in for the same 20 thou or half millimeter depth of cut, same RPM and same feed rate as before. So I can't tell if you can tell via video, the improvements that these little changes are making. But the chip now is nice and smooth. There's no more hacksaw. The only problem is it's a long, stringy chip, and as you saw, it kind of nests up pretty bad. That brings us to the last and probably trickiest part of this, chip breaking. So before we get into this, full disclosure, I've never had much luck with chip breakers in high-speed steel. I wrestled with a little bit early on, but it was just a tough nut to crack. Meaning, I'd get mixed results out of the same tool depending what I was working on. And there are other ways to sort of mitigate that chip formation that we'll get into in a minute. For now, let's imagine that this is the lathe setup. I didn't have it in me to make a Mr. Pete style gigantic high-speed steel bit. So for now, let's just assume that this is our lathe tool. And that's the work that we want to cut. So this is mounted in our tool post, and we're doing a turning operation. It's the same exact thing for facing, but we'll talk about turning. This is our chip to be. This is just some aluminum welding rod. So as that tool tip comes in contact with the work, it starts to remove material, and this is what it's peeling off. When this chip hits the work, it's got nowhere to go and it starts to bend. As the tool bit moves in and is constantly feeding material, let's say to the top of the tool bit, this just keeps sliding across the work, taking that bend, and creating that chip we all know and love. If you think about it, how tight that chip curls is a function of how fast the material is coming across the tool. So it's a function of your RPM, your feed rate, and the depth of cut. For a certain size chip, that material that you're taking off is only going to be able to accept so much of a bend. Right? If you try to curl it too tight by going too fast or feeding too fast, not too fast, but faster, that material won't be able to sustain sort of that bending and it'll start to break. Okay, so how fast you're trying to curl this chip has an effect on whether it'll break or not. Like I said, it depends on how fast the material is coming off and the material properties themselves, of course. There are some materials that are just sort of ductile or stringy. They just don't want to break. They make long, continuous chips. So instead of just depending on that speed and feed and sort of material property, some clever people came up with a geometry to help break that chip. And what that basically boils down to is a step or some other shape on top of your tool that helps put a harder bend in that material. So first it hits the top of the tool, it starts to bend. Instead of kind of doing whatever it wants after that, it hits another wall and it makes a harder bend still. Or it shoots it off in some weird direction to facilitate that chip breaking. This little step, or this little feature, every manufacturer's got their own flavor of it, is called a chip breaker. Now that said, their chip breakers will usually have published data on when that geometry actually starts to break chips. It might not actually start doing its thing until, a certain feed rate or a certain depth of cut. Now, as you can imagine, trying to build this kind of a wall or secondary step using just a bench grinder can get a little bit tricky. I've seen people do it with little zip disks. I've seen people do it on bench grinders, and it works to some extent. But like I said, I've never had much luck with it or patience for it, let's put it that way. And either have increased the depth of cut, the RPM if I could, or the feed rate to try to get those chips manageable. They might not be little C's or 9s or whatever they call them, but they're not a mile-long bird's nest. Just for kicks, let's go try a little experiment with our tool. So back at my workbench of hyperbole, I may have exaggerated a bit on the chip breaker. Well, not exaggerated per se, but definitely oversimplified. I did that to convey the concept. In real life, especially for home shop kids, chip breakers are much more subtle than that. It might not be so much as chip breaking than it is chip control. So what I did was make a very cheesy and dangerous chip breaker. Just a piece of sheet metal I hammered to shape to create a disruption in the cutting tool geometry on the top face. I'm not going to share that with you because I don't want anybody to really try to replicate it. That's not the right way to do it. We'll be doing it the proper way, at least trying to, by grinding the chip breaker into the geometry of the tool. But I didn't want to scrap this tool, have to regrind a new one, and it would look different than this one. Cause continuity problems with the video. But I want to show you the results of this. For reference, here are the chips we were getting last time we cut with the tool. Again, no chip breaker. They're all nested up and dangerous to work with. After I added my fakey chip breaker, this is what I started to get. Started off with a long coil, and I started to play with the feeds and the speeds until that coil got tighter and tighter and tighter. I couldn't go fast enough on this lathe to actually break the chip. at least with that chip breaker geometry. So these kind of chips, although continuous, they're much easier to manage. They sort of scoot right out of the way as they're being created. Now, unfortunately, in my case, I have somewhat of a perfect storm. I think I mentioned earlier that there are some materials whose, chips don't want to break. Aluminum, especially with high-speed steel, is one of those. I mean, it depends on the grade of aluminum and all that kind of stuff. And I don't want this to sound like a sour grapes. I think the ideal situation is to have chips break, but in reality, you don't always want them to break. I'm trying to think of examples, but maybe like in a boring operation where you're boring a deep hole with the tool, you may not want it to fill full of discrete singular chips. You'd rather have them sort of exit the bore as they're being cut, and that long continuous chip achieves that. Sort of like a drill bit. Drills create two long continuous chips, and usually we bump the handles a little bit to break those, just so they're not whipping around. But that's kind of the idea. It's more about controlling the chip to keep things safe than it might necessarily be about breaking them. Anyway, less talk, more action. Let's head over to the grinder and try to put a chip breaker in here and reproduce those results the proper way. All right, so this is the top cutting face of the tool. And what I want to do is grind a chip breaker sort of in that area there, because this tool primarily cuts right to left. If this were like a parting tool or a facing tool and the tip is sort of the primary direction, we'd cut the chip breaker across the front. Now I'm going to be doing this with the edge of the wheel, and in order to do this, I'm going to have to take this tool rest off. I can't get the angle on the wheel with this tool rest in place. If I were to grind it this way, I'd end up with a very negative tip on the end of the tool. So bear with me just a moment. So now I can kind of get in there tangentially. I want that chip breaker to sort of be parallel to my cutting edge, both along the tool and along sort of those rake angles we put in. Though a chip breaker ground this way is going to increase the rake of this tool. It's going to make it a much more positive rake tool. We'll see that in a second. My apologies if I sound a little bit different. Somewhere between walking over from my bench grinder to the lathe, I managed to catch a cold. I did have to go buy the milling machine. It's a little under the weather, so I'm guessing that's where I picked it up. So hopefully here you can see the chip breaker a little bit better. And if I highlight it a bit, that makes it any better or any worse. As I mentioned, the cutting edge now has gotten a lot more positive, a lot sharper. I've pretty much gone all the way up to the edge. Some people like to leave 10, 20, 30 thou. It's all sort of part of the black magic and how steady your hands are at the grinder probably. So what I'd like this to do is either break the chip or curl them nicely and get them out of the way. Essentially what the fake chip breaker did earlier. Now since this is aluminum and I'm filming it, I have a 93.46% chance of making a fool of myself. But before I start, just a couple more thoughts about chip breakers and how they usually do their thing. Like I said, what we mentioned on the bench was a bit of an oversimplification. I said when the chip coming off the work hits that feature, it changes the shape of the curl of that chip. Now, some chips do break because of that. More often than not, however, the chip breaks because it's been put sort of on a crash course with either itself, like it'll bend, hit itself and break, with the spinning work, or with the tool. Top of the tool, side of the tool, top of the insert. Basically, its path has been altered to have it run into something to cause it to break. And that's how I believe most chip breaker geometry is designed to work on insert tooling. We'll likely get a look at that when we actually talk about the insert tooling. But for now, I'm just going to fire this up, same RPM, same feed rate as before, and see what happens. In fact, if you're really interested in this stuff, it's cool to kind of go back, either look at the footage in the beginning of this video or the footage, while other people are machining, and keep a close eye on where the leading edge of that initial chip goes. Sometimes, especially when the feed rate is high, you'll see the very tip of that chip hook around and get in front of the work, like on the face of it. And as the tool is moving, what that's doing is opening that coil up. It's opening sort of the spiral. And when it does that, it sets the chip in motion to become, the bird's nest. Alright, so it actually was sort of breaking them off. A little bit past the halfway point, it transitioned into a long coil. That was 20 thou depth of cut. Let's try 30. Alright, so it doesn't like 30. Let's try 40 just for kicks. Now when it hits this shoulder, it's going to be a 70 thou depth of cut. So my lathe doesn't like 70 thou depth of cut. That 30 thou, except for a rough start though, started to get, these nice long coils. They were just feeding right down, nice and supple into the chip tray and just kind of coiling up like a snake there. So there you have it. What you just saw in the last 2 minutes is a microcosm of my 10 years of experience with screwing around with these chip breakers on and off. Like I said, I never had much patience for them because of these kind of variable results. It started off strong. I mean, it's much better than no chip breaker in this case, right? It was making these long, controllable chips of, varying quality, which is worlds better than these bird's nests. Now, without the chip breaker, by playing with the feeds and speeds, you can get close to this without having to grind the chip breaker. Chip breaker is probably the easiest way to get there, but if you don't have the patience for that kind of thing, either move to carbide inserts or play with your feeds and speeds a little bit more for the diameter of your work and see if you can't get to a sort of a more controlled chip, a safer working condition. Before I close this out, I just want to mention a couple of things I sort of glossed over. Now, if you've watched other videos or seen pictures of these online, you might notice that my tool bit looks a little funny, maybe a face only a mother can love. And that's sort of a function of how we got here. Now, I sort of took that Scooby-Doo mystery solving approach, and we took every grind more or less independently of the other grinds. In reality, when you set out to grind a tool, you'll probably know exactly what you want it to look like before you even turn on the bench grinder. In addition, we've left off the side edge angle. There's a sort of a lead angle that's usually built into these tools. Would have probably helped in this case, to be honest. But again, it didn't really come up in the approach that I took. If I'm not mistaken, for this type of tool, there are sort of 7 key data points that fully define it. It's those 3 relief angles, the 2 top rake angles, that gets us to 5. The nose radius is 6, and sort of that lead angle is 7. So if you were to call up like a custom cutter shop and ask them to quote you this style of turning tool, after they got done laughing, they'd probably ask you for those 7 dimensions, those sort of 6 angles and the nose radii. And then they'd probably tack on another $100 to the quote just for wasting their time. All right, I think that just about covers what I think I know about high-speed steel. Again, my intention wasn't to make a tutorial per se. It was more to sort of walk our way through why the various clearance angles and relief angles exist. We ended up with more of like a shaper-looking tool bit than a lathe-looking tool bit. But hopefully this gives a little insight into what those clearances and rakes can do, and that way you can apply it to any type of tool that you'd like to make. I mean, that sort of basic single-tooth, single-point cutting geometry applies to everything. Lathe tools, table saws, chainsaws, cold chisels, drill bits, end mills, you name it. Just think about how you're approaching the work, how you'd like it to cut, and where you would need clearance and relief. And if you follow my channel, you may have noticed that I use insert tooling almost exclusively these days. I still keep plenty of high-speed steel on hand. It's indispensable for custom cutters, and in my case, essential for the shaper. But this video's gotten long. I'll follow this up with a quick chat on insert tooling from a hobby perspective, for whatever that might be worth, and how that switch happened almost unconsciously for me. So that's it. As always, smell you later.